Alrighty, nerds. We are going to finish up unit 3.5, sinusoid functions. And basically today we're going to be talking about frequency, and we're going to start dipping our toes a little bit more into modeling. So that ought to make some people happy, like Isabella over there when she was talking to me about the, remember the Ferris wheel question? Okay, I'm going to mention it today, and after today's lesson, questions like that will be easier. Okay? So we've talked about amplitude, period, midline, concavity, phase shifting. The very last thing that we need to talk about as far as characteristics is concerned is the frequency. And the frequency is a very easy thing to find. It's literally the reciprocal of the period. Ta-duh. That's it. So the period length is how long it takes for one full cycle to occur. The frequency is the number of full cycles that occur within a given amount of, let's say, time. It's literally just the reciprocal, and that's it. So you find your period length and flip it over. The hardest part about frequency is analyzing what it means in the context of a situation, in the real world situations. That's it. That's the hardest part. So let's take these two sinusoids here. It says use the equation, find the period and the frequency. All right, easy peasy lemon squeezy. The period is, oh, by the way, you know, I say 2 pi over b. I'm aware there's absolute value bars. I never write them because just like my amplitude, I know that the number that sits in front of things is going to be a positive number as a transformation, because the negative, if it exists, has nothing to do with the width or the height of the object. The negative would simply be a reflection. So I just basically ignore it when I'm thinking about heights or widths. Cool beans? So just forgive me, I'm never going to write the absolute value bars. I just don't. Anyway, period length is 2 pi over your b value, but dividing by 1/4 is the same as multiplying by 4, so we get a period length of 8 pi. And a frequency, which I'm just going to write as freak, a frequency of 1 over 8 pi. And without a model, it's kind of hard to talk about what that means. I don't know, what is 8 pi divided by 1, or 1 divided by 8 pi? Okay, that's 1 divided by 8 pi. So this says it takes 8 pi for one cycle. And this says there are 0.0398 cycles per 1 unit. That's all that says. So you just basically read it backwards. Makes more sense when you have a real world question to discuss, like waves occurring across time at the beach or something like that. Makes more sense. The b value on this one is 48 pi. The pi's cancel, and you get 2 over 48, which is 1 over 24. This means that a period length is 1/24th of a unit. So if you're on the x-axis, you're going to go from x equals 0 to x equals 1 over 24 for one cycle. But the frequency then, the reciprocal of 1 over 24, that's 24. What that tells you is, if you go on the x-axis from x equals 0 to x equals 1, you will have completed 24 full cycles. So there are 24 full cycles per 1 unit of the x-axis. This says it takes 1/24th of a unit to complete one cycle. Basically, because they're reciprocals, a large period means a small frequency. A small period means a large frequency because they're reciprocals. Neat idea? You good with that? Nobody seems concerned. I'm good with that. Then A physics question. You see these a lot in physics. A mass on a spring oscillates back and forth and completes one cycle in 0.25 seconds. Pump the brakes. Stop. What knowledge were you just given? The period length. The period length is 1/4 of a second. Its maximum displacement is 6. Pump the brakes. What was that? It's the maximum or the minimum, which means the amplitude. So we were just told that the displacement, the maximum displacement, which means the furthest it's going to go from its middle, is 6. That could be 6 up, that could be 6 down. You weren't told, and that doesn't matter. The point is, you can only get 6 away from the middle, therefore it's the amplitude. It says, write an equation that models this motion if the spring is released from its maximum height. And then we'll find the frequency. I never try to find the equation of a sinusoid without sketching its graph first. It's showing you that this is 0. This is not a height. This is an amount of displacement. So basically, if you attach this thing to the ceiling for some strange reason, I don't know, physicists are always talking about masses bouncing around on springs. Anyway, if you attach a spring to the ceiling and it's got a weight on the end of it and you slowly lower it until you could feel that it's not lowering anymore, and it would just sit right there. Now it is still hanging from a spring. So if you pulled it down and let it go would go boingy, 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 boingy. And what we're going to say is we're in a frictionless vacuum and the spring oscillating would not create heat. Therefore, no energy would be lost through sound, friction, or heat. Therefore, it would boingy, boingy, boingy for all eternity. Up and down, up and down, up and down. Okay? All right. That means we could graph a sinusoid and its default displacement is no displacement at all. That means that's our midline. Are all midlines going to be 0? No, of course not. Not at all. I mentioned Isabella's Ferris wheel question a little bit ago. Well, more than likely that Ferris wheel question, its midline was not at 0. Okay? But this one is, because we're talking about displacement. And it says that it's released from its maximum height. That means it's released from up here. So if I wanted to sketch that graph, it'll do this. Maximum height. And bounce back up to maximum height. So what would be the easiest style of model to use? Specifically, positive cosine. So this looks like a positive cosine. Because it says it's released from its maximum height. And we already know the midline is 0. We darn near have the entire equation. Its displacement over time is the amplitude of 6, and it's going to stay positive 6 because we said positive cosine. We know that the midline is 0, so there won't be anything added or subtracted at the end. And there's going to be some number in front of t. All we have to do is figure out what that number is, and we can use this to figure that out. Because the period length is 2 pi over b. Trying to figure out what color I want to write with. We know that 2 pi over b is 1 over 4. And how do we solve a setup like this? Yeah, but how? Cross multiply. Yeah, we're just going to cross multiply. And that's going to give me b times 1 equals 2 pi times 4. Oh, b is 8 pi. There you go. That is the equation that models this thing's displacement over time, assuming it was dropped from its maximum height. Great. Lastly, it says find the frequency. Well, the frequency is just the reciprocal of the period length. So since the reciprocal was 1/4, what is the frequency? 4. Now we need to use units because this is AP. So this 1/4 of a second, that's actually 1/4 of a second per cycle. So this 4 is actually 4 cycles per second. So this thing is bouncing really fast. Boing, 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 boing. 4 full patterns in 1 second. That's what the frequency is. What do you think about all that stuff? Not the worst, right? Let's take a peekaboo because I've already mentioned it at that question that Isabella was talking about. This thing's midline would have been the center of the system. Remember, I said midline's not always going to be 0. This thing's midline was not 74. What you were being shown is that from here to here is 74. So half of it, the radius, would have been our amplitude, was a 37, right? But this is a 6. So the midline for this system is actually 6 plus 37, which is 43. Now, I'm just going to sketch the graph of this thing for us, okay? It says, well, let me ask you. If you get on a Ferris wheel, where on the circle would you typically be when you got on? At the bottom. So if I was going to sketch this graph, I would start at the bottom, which is 6. Eventually, I would be at 80. But if I start at the bottom and end at the bottom, then a negative cosine wave would have been the best model for this. Where the radius was 37, so it actually would have been negative 37 cosine of blah, 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 and the midline was at 6 plus the amplitude of 37 plus 43. So there's the majority of the equation. Now you would just say, what is it? 48 seconds is what it says, and you would go 2 pi over b equals 48 to figure out what number sits in front of t. But that's how we do these modeling questions. I would never try to write an equation without a picture of its graph. That's just how I've always done it. Because then I can see what kind of a model is the easiest to use. And if I see it, I'll even tell you, I've seen IB questions that would have perfectly modeled themselves as negative cosines like this, but they specifically say find a model of the form A times the sine of yada, 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 forcing the IB student to write it as a sine model instead of a cosine model. So if we were going to do that, then what you would do is go, fine, I'll say it's a sine model that's been shifted to the right 1/4 of its period length, which would have been 12 seconds, because that's 1/4 of 48. And again, I can only do it that fast with a picture. Without a picture, I'm wrecked. I have to draw a picture. But I'm hoping that that helps, Isabella. I know it's been a long time since you asked, but I hope that that kind of clears up all those mysteries. Cool beans. Whee! Okay, let's move on. All these words basically say, instead of saying maximums and minimums, you could say upper bound and lower bound. And instead of saying midline, you could also say equilibrium. Yeah, I've never heard the word equilibrium used in trigonometry ever. I highly doubt that that'll be on the AP exam. But just in case, I'm hoping that you all understand that an equilibrium pretty much means in the middle. And that you could use a little bit of common sense and knowledge of the English language to go, oh, in the middle, the midline. Upper bound, the highest. Lower bound, the lowest. Okay? All right. And I'm going to make life really good. We're not even going to do all three of these. Because why bother? They're all the same skill set. If you could do one of these, you could do any of them. That's what's great about sinusoids. If you could do one, you could do all. It says, consider the first period and the first period only. So do yourself a favor. Do not even see that, okay? It's the first period only. It says, find the 5 key points for a single period. I'm not going to write them all down. I'm just going to circle them. Because they're literally minimums, maximums, and midline hits. Regardless of where that midline is. All three of these examples, the midline happens to be on the x-axis. That just means they weren't shifted up and down. It doesn't matter. As long as you understand what really important thing is always going to happen at the midline. An inflection point. Every time a sinusoid hits its midline, you have an inflection point. So it doesn't matter that it was an intercept or not. The point is, it was the midline. So every time you touched it, inflection point. Cool? All right. Okay, so we've done part A. Part B, identify concavity, up and down. So where are we concave up? Well, right there. That's concave up. And obviously, that zone of concavity would repeat itself every period length. Whatever the period length is. Looks like the period length is 2 pi over 3. But it just says for one period. And where are we concave down? Well, the other side. Right there. So from 0 to pi over 3. Please remember, we do not use brackets on concavity. Now part C says, what about increasing and decreasing? And for some reason, we've chosen to use brackets on that, but not concavity. I still don't like it, but I just want to make sure that you get things correct on your AP exam. So where are we increasing? Well, increasing would be remember, if you were riding this thing like a roller coaster from left to right, it'd be any time your roller coaster was going up, or you could just say anywhere where you see positive slopes. I see that happening in 2 places. There's one of the places. Ta-da. And there's another place. Ta-da. So we're going to have to put a union between them. So we're going to say we increase from 0 to pi over 6. And also from pi over 2 to 2 pi over 3. Decreasing is the places where you're not increasing. Oh, there it is. So from pi over 6 to pi over 2. When it says name the points of inflection, I'm just going to say the midline hits. Or you could say x equals 0, x equals pi over 3, x equals 2 pi over 3, so on and so forth, whatever. So there's me naming them, but obviously it's just going to be any time you're on the midline, okay? Nobody cares what the y value is. The point is it's the midline. And the other 2 examples are exactly the same. Nothing different about them. Yes? Oh, well, it'd just be 0, 0. Oh, if you wanted to write it as a pattern. Well, it appears as, so basically it works like this. A sinusoid hits its midline every half period. Right? And that's true for sines and cosines. Like, look at this thing's period is 4 pi, right? It hits the midline here and here. Distance of 2 pi. So midline hit to midline hit is always half of a period. So if you wanted to write it as a set of repeated points, you could write it like this. 0 plus or minus, and it looks like half of our period is pi over 3. So it would be like pi over 3 in, and then they all have the same y value. And this would be where n is an integer, like that, if you wanted to do it. Because it's showing you every time you go pi over 3 left or right, you're on the midline again. So you have another inflection point. So half period. You hit the midline every half period. Cool? Okay. That's a good question. Nobody asked me that in period 2. That's a good question, though. Word problem. Immediately there's an issue. Let's see if any of you sees the issue. So what we have here is a buoy oscillating as waves go past. Anybody see the issue? Period 2 saw it fast. No? Look where the word equilibrium is. Oh. It's not on the midline. So it's just been copied and pasted in the wrong spot. Equilibrium's in the middle. It's the midline. So we'll put it here. There. Okay, let's read it. A buoy oscillates as waves go past. For any given time, it moves a total of 4.5 feet from its lowest point to its highest point. Stop. Its lowest point to its highest point is 4.5 feet. What can I do with that knowledge? Yep, I can cut it in half to get the amplitude. Amplitude is 2.25. So it's at its high point and then returns to that high point every 15 seconds. What does that mean? That's the period. So the period is 15 seconds. We know our amplitude, we know our period. If the buoy is at its lowest point at time equals 0, oh, we're starting at a minimum. We're going to write an equation that models the motion. We're going to start at a minimum. However, before I do anything, we need to talk about what we agree to let the equilibrium equal. If the sea was flat calm, what would the height be of, yes, it'd be 0. Did you guys know that a height of 0 is sea level? That's what that means? Okay. So equilibrium is going to be at a height of 0. Okay. So I'm not going to try to write an equation until I have an image of what's going on. I've got this. I've got y equals 0 being my equilibrium. I know my amplitude is 2.25. And I know it takes me 15 seconds to complete one full cycle. I'll draw in blue because it's a wave. And it says we start at a minimum. That means we end at a minimum. So what would be a very easy model to use? Negative cosine, because it's upside down. A negative cosine model would be the easiest. So we're going to say the height of our buoy over time is negative amplitude cosine of, I know the variable is time, and because we've said that equilibrium is going to be at sea level, which is a height of 0, I know that there's no vertical shifting, plus or minus at the end. It doesn't exist. All I need to know is the b value, the number that sits in front of t. 2 pi over b equals 15. So 2 pi over b equals 15 over 1. If you do the cross multiplication, you get 15b equals 2 pi. So what does b equal? 2 pi over 15. It's not pretty, but whatever. There it is. An equation that models the height of this buoy over time, given that we start looking when it's at its lowest point. Neat. It says, what is the frequency? Yeah. The frequency is 1 over 15. But it says explain that in this context. So this means there is 1 wave every 15 seconds. That is what the context is. The period is it takes 15 seconds to get 1 wave. The frequency is there's 1 wave every 15 seconds. Or you could say there's 1/15 of a wave every second, if you wanted to think of it that way. It's a little strange, but I think it's easier to think about it like that. I'm going to ignore part of the directions for part C. The part that says use a graphing utility. You don't need one. It says use a graphing utility to find the point of inflection where the buoy is at equilibrium. But tell me, on every sinusoid, where are my points of inflection? On the midline, which so you're not wrong, which you were talking about the quarters, but it's going to happen at the midline. So I've already sketched this graph. We can already see where we're on the midline. Right there. That's halfway between 0 and 7.5 seconds. Anybody know what half of 7.5 is? 3.75. Well, 3.25 times 2 is 6.5. Okay? Remember half of 7 is 3.5? Okay. So you're at the inflection point at time equals 3.75 seconds. And again, every, how often? Not 15. Huh? 7.5. Because remember, you are on your midline every half period. You're at your maximum to maximum every full period, minimum to minimum every full period, but midline to midline is only half of the wave. Okay. So first time is at 3.75 seconds, and then every 7.5 seconds later, we're at an inflection point again. What does equilibrium of the buoy mean in respect to the behavior of the waves? I mean, yeah, I mean, like you could say that this is where the waves are technically flat. You could also say where the waves change from going down to going up, or going up to going down, if you wanted to. Yep.
You said when it's over or under sea level?
Or you could say it's above or below sea level. There's all kinds of things you could say. So you could say, what does equilibrium mean with respect to the waves? It's when the buoy, how do you spell B-U-O-Y, is above or below sea level. Or you could say equilibrium is where the buoy is at sea level. Or from equilibrium, we're either going above sea level or going below sea level. It just depends on which part of the wave we're on. There's all kinds of things you could say. And then the last part says, identify the intervals where the buoy is decreasing. Okay, well, we've already drawn the picture. In one cycle, where is it decreasing? Well, from 7.5 to 15. Because after 15, you're going to start going up again. So our wave height is decreasing from 7.5 up to 15. And how often would this repeat? Every period length, every 15 seconds. So 22.5 to 30, and then 30 to 37.5, so on and so forth. Just repeats itself every 15 seconds. That wasn't too bad, was it? Thanks, nerds.